Welcome to the first lecture of the direct stiffness method. So, let's begin. For design of different structures such as RCC, steel, timber, the design formulas and methods may vary, but for the purpose of analysis, we can see that the methods don't depend on material types such as RCC, steel, or timber, etc. And all structure analysis methods actually depend on assumptions, and the lesser the assumption, the greater the accuracy, and greater the or more the assumptions, the lesser the accuracies. So the method that has less assumptions is the most accurate method. So out of all the methods till date, Hardy-Cross method, also known as the moment distribution method, is the best method for doing structure analysis by hand. However, the direct stiffness method is the most accurate method, but the problem with it is that it is quite difficult to use in hand calculations or by hand. That is where the need for software application comes in, or computer programming comes in. Okay, so all modern day softwares use this method for the purpose of analysis, and you may know of it as the FEM. You may know of it as the FEM, or finite element modeling. So all the softwares use FEM, finite element modeling, where the direct stiffness method is used for the purpose of analyzing structures. Okay, all right. So depending on the material property, analysis is actually of two types, linear and non-linear. So as long as the material stays within the elastic limit, within the elastic range, the linear analysis is carried out, and if the structure does not, or the material does not stay within elastic limit, then non-linear analysis is carried out. Also, depending on load type, the analysis is of two types. One is static and another one is dynamic. So the static load, the load that does not vary with time, is actually the static load, and the dynamic load is the load that varies with time. So an example of dynamic load can be earthquake load. Okay, so in this course we're going to be doing linear and static analysis. So we're going to be doing linear and static analysis, also known as the LSA in short. Okay, we're going to be doing that. So here are some short notes. There are some differences between linear and non-linear. We have just said that linear stays within elastic range, the materials, as long as the materials are staying within elastic range, they're linear, and then non-linear is when they do not stay within elastic range. Now note that in reality all materials are non-linear. We're going to be talking about that later on. So let's take a look at the difference with the analysis and design. So what is analysis? In analysis, you give some input and get some output. For example, we give material property. For example, which kind of material we are using. Are we using RCC? Are we using steel? Are we using timber? So these are the material properties, and then geometry. We give it the geometry. For example, if I consider an RCC section, let's say of 12 inches by 14 inches, and then it is of length, let's say 20 feet. So let's say this is a beam of 20 feet having a cross section of 12 by 14. So that's its geometry. And then we also have applied load. For example, if this beam is subjected to an UDL, then this is the input. So this is the input. This right here is the input. For this input, we're going to determine some output, and that output can be ASD, axial force diagram, SFD, shear force diagram, BMD, bending moment diagram, or torsion. For example, if we want to draw the shear force diagram for this, we analyze it for these conditions, this inputs, we analyze it for that, and then we get a shear force diagram, the SFD. So this is the output of the analysis. We can also get the BMD, the bending moment diagram. This is also the output of the analysis. And on the other hand, the design is actually based on this analysis. So it says that on the basis of analysis section, material and geometry is decided. For example, when we analyze this beam, this 20 feet beam, we see that the highest moment is at the center. The highest moment is at the center, and that is why we decide that we're going to use bottom bars right over there, or we're going to use 2 to 3 bars, or the number of bars which are being decided by the amount of movement here. And if we're not doing RCC, if we're doing still, if we see that the bending moment is of value x, and the still section that we had initially chosen can only take loading less, which is less than x. In that case, we have to change that section to another section that will be able to take loads greater than x. Okay, so that is design. On the basis of the analysis, we decide something or we change sections. That is the design. Okay, then the difference between a truss and a frame. So the truss has pin joints where frames have rigid joints, and then trusses are two force members, and where the beams are actually have internal forces like shear force, and the frames, sorry, not beams, the frames have shear force and bending moments and etc. So truss only has two forces. It can be either compression, it can be either tension, but the frames actually have internal forces. Okay, after that we have static load and dynamic load. We have already covered that. Let's move on. And this is a small difference between kinetics and kinematics. If you want, you can read it out from here. Okay, now to the node that we are talking about, that in reality all materials are non-linear, right? So if you look at this diagram, so if you look here, you can see, and you can say that, hey, concrete right over here is linear, right? The concrete right over here is linear, but if you look into it in great detail, you can see that this curve is actually not linear. You may say, hey, this is linear till this point. Till this point, this is linear. But in actuality, that is actually not linear, because if you zoom in, you can see that this is not linear. There is a certain curve there. When will it be linear? If I take a small portion, like if I take this particular small portion, then this part can be considered as linear. But again, this is just in consideration. This is actually not linear. This is non-linear. Even if it's non-linear in a very micro scale, that's still non-linear, not linear. So that is also an assumption that we take, that it is linear, but that it's actually not linear. Now if you take a look at the stress strain diagram of steel, you can say that, hey, this line till this position is linear, right? You can see the rise and the run, so this is linear. But this actually is not linear, because if you look at the diagram on the left side, which is the same diagram for the steel section, you can see in this diagram there is a straight line. A straight line has been drawn here. On the other hand, if you look at this diagram, you can quite easily see that this is not quite a straight line, right? There are little curves, little bumps here and there, right? So it's actually not that linear. But how will it be linear? It will be linear if we take a small portion. Again, if you consider, let's say, this small portion from here to here, if you consider this particular small portion, then we can say that, hey, this is linear, or at this location this is linear. But if we look at it in a nanoscale, we can see that it's still not linear, it's non-linear. That is why in reality all materials are actually non-linear. Okay, so that's it for lecture 1. Thank you very much for watching.